All right, so this is video 3 for Topology of the Reals, part of the Baby Real Analysis YouTube playlist, and the last video ended up being longer than I was thinking, so I wasn't able to do this problem. So I saved it for this video, exclusively going to be about proving the open interval AB that the subset of the reals is open using the Euclidean metric. So I ran out of time in the previous video, but I can use the kind of mimic this proof. This is the proof in video 2 where I showed the open interval 0, 1 being open. And how I did it was I picked, so P was any number in 0 to 1. I needed to show that there exists an epsilon neighborhood of P that's contained in 0 to 1. And so I used the definition of neighborhood, and then I wrote that as this compound inequality statement. And it's another way of saying I need to show that every point P is an interior point of 0 to 1. So for this neighborhood, epsilon neighborhood of P, I had an arbitrary, and again, P is some arbitrary value that's fixed. I can find any value X that's in the epsilon neighborhood of P such that X is in 0 to 1. Or 0 less than X less than 1. And the epsilon neighborhood that worked was using the minimum of 1 minus P and P. So if I had, the open interval 0 to 1, and then P could be anywhere in here, say that's P. And we have the distance from P to 1, that distance is 1 minus P. And then the distance from 0 to P was P minus 0, but that was just P. And then I essentially said, all right, let's use the smaller of the two to guarantee that the epsilon neighborhood still lies inside 0 to 1. I'm going to mimic this. Again, this is on video 2 that I wrote this out. I'm going to do a similar thing here. I just want this video to be short in this sense compared to the other first one and second one. So we're just focusing on this proof of the open interval AB. I'm going to mimic what I did with the proof for the open interval 0 to 1. All right, so the goal is to show that for all C and AB, there exists an epsilon so that the epsilon neighborhood of C is contained in AB. Well, the epsilon neighborhood of C is a set of X such that the absolute value of the difference, X minus C, is less than epsilon. And I just rewrote this into this compound inequality as C minus epsilon less than X less than C plus epsilon. All right, so for the proof, again, I'm going to pick any C that's an element of AB. All right, so A less than C less than B. I'm going to need to show there's an epsilon neighborhood of C that's contained in AB. And that epsilon I'm going to use is similar to what I did with this one, the 0 to 1. So here's A, here's B, say this is C. And so I have the difference for this one. And so B is bigger than C, so B minus C is bigger than 0, so that I could use that as my epsilon. Or since C is bigger than A, then C minus A is bigger than 0, and I could use C minus A as my epsilon. And what I did with the 0 to 1 was I used the smaller of the two. So that's what I'm going to do here. So let epsilon be the min of C minus A and B minus C. And we know this is bigger than 0 since, well, C is bigger than A. So C minus A is positive. And then B is bigger than C. So B minus C is positive or bigger than 0. So like last time, I'm going to break it up into two cases. Let's say the case one, let's say the min is, let's go with the first case. Let's do C minus A. All right, well, okay, so say the min is C minus A. Well, then, because that's the min, that's less than B minus C. And I'm going to basically use the statement that for all x in this epsilon neighborhood around C, we know the compound inequality C minus epsilon is less than x, less than C plus epsilon. So if epsilon is C minus A, then we can state that we have C minus parentheses C minus A less than x less than C plus C plus C minus A. And we know that is, make sure I have everything. Well, we know that's less than. So C minus A is less than B minus C. So if I add, so using the fact that C minus A is less than B minus C, then if I add C to both sides, C plus C minus A is less than C plus B minus C. And so I can say this is less than C plus parentheses B minus C. All right, so what does that give me? So then we distribute the negative, so this C and C cancel, this becomes A. So it'd be A less than X, less than 2C minus A, and then less than, this becomes, so B and, or C and negative C cancel, so you just get B. All right, so A less than X, less than B. Let me erase this part. All right, so X is in AB. So we've shown that for this epsilon being C minus A, that was the minimum of C minus A and B minus C. So we've shown that for any X in that neighborhood of C, epsilon neighborhood of C, we had that A is less than X, less than B, which means X is in AB. But X is arbitrary in the epsilon neighborhood, so that means that the epsilon neighborhood of C is contained in AB. All right, so that's when the min is C minus A. So let's do it where B minus C is the min. All right, so case two. So say the min is B minus C this time. And B minus C, so that means B minus C is less than C minus A. And if that's true, if I multiply both sides by negative, then I could have negative times B minus C is bigger than negative times C parentheses C minus A. And if that's true, then I could add C to both sides, and it'd be C minus B minus C is bigger than C minus parentheses C minus A. And so then that would, you'll see how I'm basically going to use this statement and substitute epsilon being B minus C. All right, and so the statement C minus epsilon less than X less than C plus epsilon, that's going to become C minus parentheses B minus C less than X less than C plus B minus C. And we know that C minus parentheses B minus C is bigger than C minus parentheses C minus A. So I could add on to here on the left the inequality that C minus parentheses C minus A is less than C minus parentheses B minus C. So C minus parentheses C minus A. And what does this turn into? So we get the C and negative C cancel out, distribute negative, negative A times negative becomes A. So it'd be A minus, or A less than, and here would be B minus 2C, or 2C minus B, less than X, and then less than B. And so A less than X, less than B. All right, so that means X is in AB. Okay, so again, for all X in the epsilon neighborhood around C, and in this case, the smaller of the two is B minus C. We had A less than X less than B. And that means X is in AB, but X was arbitrary in the epsilon neighborhood of C. And so the epsilon neighborhood of C is contained in AB. And this is true for all C in AB. Right, C was just some fixed arbitrary value in the open interval AB. So for since I did that for all C, I can do that for all C, then it's an interior point. All the points are interior points of AB. All right, so that completes the proof. Maybe these are extra details and necessary, but I hope that makes sense. This is I just wanted to keep the video at that. It was just proving the open interval AB and the reals is open and basically mimic the proof that I did in the previous video where I proved the open interval 0 to 1 was open.